Before we start going here, any questions about anything? Current PA, midterm Friday. Everyone happy with the PA? Everyone's happy with the PA. Anyone unhappy with the PA? Unhappiness, unhappiness. Are there questions that go with the unhappiness? Just general unhappiness that I cannot solve. Yeah. So the way we talked about this in lecture and what the PA expects is that when our main is defined, there is always a parameter called input. So whatever happens in the body here, there's always this parameter called input, and the combination of the main function in main.c and our code starts here sets things up so that this is like any other function call in the language we're implementing, and input is on the stack at the right spot to be an argument to that function. So depending on how you set up functions that you implement, right, you'll have to pay attention to that prelude of assembly instructions that we provided for exactly where it's grabbing this input value from main. Does that answer your question? Okay. So the way we set up the PA, and this mirrors what was in the notes from last week. Pretty, like, the most clear one is the notes from last Wednesday, where the main function calls some parsing on the integer, then it passes it to our code starts here, then our code starts here, sets up a our calling convention stack frame for our main. Right? Whereas our code starts here is acting kind of like a C function, and our main is acting like one of our functions. Right? That's sort of the reason there's that little bit of fixing things up as we go between. And that's something I mean, that's a general compiler's thing that happens when you have multiple languages interacting. When you go back and forth between them, you sort of fix up the stack or fix up whatever state there is to make them sort of mesh together. Question? Your function body will care, right? So, right, but we don't care if you do it pushing them from left to right or from right to left. It just has to be consistent. It just has to be consistent. There are some interesting design decisions there. For example, if you want to support later on functions that can take any number of arguments, there's some questions about if it's better to push right to left or left to right. For these where there's a fixed number of arguments, it just has to be consistent. I mean, I had to pick something for lecture, right? I couldn't do both, right? So I did it left to right, right, in lecture. Because it was like, also in lecture, since I was doing EAP2, it sort of nicely mirrored the code of ePrim2, right? So it was like evaluate the left-hand thing, evaluate the right-hand thing, push them both, and then move them around, yeah. But you're right, either order would make sense. The one thing that I will point out is you should evaluate them left to right, right? Like if there's two parameters and they both print, right? Both are expressions that print. They should print left to right, but then you can put the values that result on the stack in any order, right? So to be clear about what I mean by that, let's say you had a function f, and I'll write it in the syntax of the PA. And it takes arguments a and b. It doesn't matter what f does for this example. And then somewhere else in the program, in main or somewhere in the program, you call f, and the argument expressions to f are prints. Right? The PA and us as a staff and me in terms of what I want you to demonstrate, I don't care if 1 or 2 goes onto the stack first, right? That's up to your calling convention. But 1 should print before 2. right? So the expression should evaluate left to right. But it doesn't matter in terms of the calling convention which order the values end up on the stack. Right? So that's a useful distinction. Different languages have different specifications for what order these things are supposed to evaluate in. We expect them to be evaluating left to right. Other questions? Yeah. So print should print the value you give it and then return the value you gave it. Yeah. It should have been in the write-up. If it wasn't, it's a mistake. Yeah. Yes. A sample of them do. Like all the ones that do function calls run Valgrind. And then we took a handful, something like 10 or 20 of the old tests and added Valgrind to them. So we basically just turned T into TVG for some of them. And then the others are pretty much the same or slightly tweaked versions of old tests. It's about 100 points for function calls and then like 110 for all the old stuff being ported over correctly. And about 100 something total points run Valgrind. Yeah. Oh, yeah. So that's a really good point. It ended up being that there was a lot of stuff we tried to put into this PA, and so I took that out. The next PA, what we're going to do is give you buggy compilers, and you're going to write tests that detect the buggy compilers. So part of your grade will be how well your tests sort of cover things. And the next PA is actually going to be just about writing tests. You're not going to implement a compiler next week. It's part of how we're going to make things a little less crazy around the midterm test. Other questions? Okay, cool. Good questions, folks, to ask them. So just two minor things? Just one minor thing, I guess, that I want to put on here so people who read this later see it too. So there's no discussion on Friday. We're going to take the time to be grading exams. So no discussion Friday, May 4th. And there's a form out for if you want to get a left-handed seat or an aisle seat for different reasons for Friday. So there's a form out about that. We'll be releasing a seating chart for the exam probably tomorrow, and we'll just release it via the secret numbers that you have that we're using for anonymized grades. So if you need a left-handed seat, we're going to close that form tonight. So just some logistics things for Friday, and then discussions will pick up after. And the discussions are often for giving examples of the PA. In this case, the PA is about writing tests, so, and it's open collaboration. So you'll be writing a lot of programs in the language, and then the next week we'll be actually implementing it. All right, okay. So Monday, we talked about a new idea. So we sort of generalized our calling convention to 2 arguments, and then we talked about a new idea called tail calls at the end. I want to say a little bit more about tail calls, sort of motivate the idea of tail calls a little more, and describe how we came up with this, this TC parameter that we're passing around with true and false inside the compiler. And so I want to do that by talking about a few different kinds of function calls. So here's a little example program. And this is just 2 functions. One of them doubles its sorry, let me just do plus here. One of them doubles its input, and the other one calls double twice, right? So this is just a nice simple example to show us using using the same function in two different places within the body of quad. We're using double on n and then double on the result of it. And there's an interesting difference between these two calls. An interesting difference between this call to double here and this call to double here. And the interesting difference between these is that the inner call to double, so the green one, the one that's passing n as an argument, we definitely need to remember the result of that call and use it in some other expression inside quad. Say that again. We definitely need to remember the result of calling double on n and use it in another expression inside quad. If we think about this program evaluating, right, if we think about a particular call to quad, we can think about this in terms of substitutions. Actually, a helpful way to think about this. This is double of 10. And when we take the next step, it's really clear that to evaluate this call to quad, we have to evaluate double of 10 and remember that there's this other double waiting to happen, right? We're going to go do this function call, which is going to be an evaluation of calling double, right? It's going to do plus 10, 10. And we needed to remember, we're in the middle of this other processing, this other function call. This is just an argument for this other function call. We have to remember something. This, in particular, we have to remember sort of this context outside that we were waiting for an argument to this. Okay. Once we're done with this step, right, once we get to this step where we're doing double, and then we're going to be doing double on 20. Once we get to this step, there's no like context or more information we need to remember about what's next for processing the answer for quad. We do double 20, and whatever answer we get for double 20 is the answer for this call to quad. We're processing this call to quad. As soon as this double 20 call is done, that's the answer for the entire function call to quad. That application, its answer is the answer for quad. That's a really fundamental distinction between the green call and orange call. One is happening in a context where we're going to use its value in this function later. And the other is just the answer for this function call. That outer call to double produces the answer. Double ends up, if we want to just produce all the steps here, this ends up evaluating all the way down. Now, that's the sort of substitution-based way of thinking about this evaluation. We used that sort of understand OCaml. This is, I always find this to be a useful model for thinking about how things evaluate, because I don't have to think about like stack layout to consider what this program ought to do, right? This program ought to evaluate to 40, and here's why, right? And I didn't have to like imagine the entire calling convention and stack layout to process in my head what I expect the answer to be, right? Or even to write out on paper what I expect the answer to be. If we think about this in terms of the first calling convention we implemented and sort of like the calling convention you'll be implementing you're in the middle of for PA3, the picture for this as it evaluates, right, we start with, we think about, what I'm thinking about is sort of starting at this call to quad 10. So we start with the old EBP value. We have the return address of wherever we are in quad 10, right? Like wherever the call to quad 10 is happening. Push the argument 10 onto the stack. There's going to be some number of local variables created for quad. So this is the local variables for quad. Then we're going to push on another return address in quad. Oops, sorry, another old EBP and then a return address. and then a 10. And this is what we're passing in to the call to double. This is how we call, how we're going to call double. And then there's going to be some space for some local variables for double. So far, so good? Any disagreements with the picture so far? Looks like what you expect? Okay, so this will do this evaluation of the call to double. It's going to add 10 and 10 together, put 20 into EAX, and then we'll jump back down to processing the instructions for quad, right? After we've done the first call to double, we're going to come back to instructions for quad. We can think about being done with this stack frame for double, because we're sort of done processing it. We calculate the 20. The 20 is going to get stored somewhere in a local variable inside quad, right? We're going to sort of store as an intermediate value this 20 somewhere in here, because that was the result of the first call to double. And then we're going to process another call to double. We did double, we got its answer, we stored 20, and now we're going to process another call to it. And in this one, we're going to have, again, a stored value of EBP, a return address, and now this time the argument is 20. We're going to double 20 just by adding 20 to 20. We'll get 40. And if we think about the instructions that are going to run once we get 40 into EAX, well, there's going to be this inside double somewhere. At the very end, we're going to call ret. We're going to use the ret instruction, which is going to return control back to the stack frame for quad. Also, somewhere in quad, there's going to be some call into, somewhere in quad, there's going to be a call over to double. And when we're done, we're going to end up returning, expecting that the answer we got from calling double is in EAX now. Basically what happens at the end of quad is we say, all right, call double, the answer's in EAX, now we can return. This means the answer we get from double, so at the end here we end up with EAX equals 40 in this particular case. The answer we get from double, we use this return address so that we can get back to right after the jump double, right? There's going to be some after call here, and then we're going to process the ret. That return address took us to after the call to double in quad. Then immediately, with basically no more work, maybe like one instruction to fix something about the stack, we're going to go and immediately return to wherever we called quad from, right? Somewhere else there was a call to quad in the program. And there was an after call for that. And then there was, well, a ret or whatever happens right after that call, right? Whatever context we called quad in. It's really kind of, the interesting observation to make here is, in between returning from double, right? So we return from double, and then immediately we're going to return from quad. In between here, we didn't use any of the local variables that we'd stored or any of the arguments in quad. In between the return from double, that second double, the one that I underlined in orange, right? The return from the second call to double and the return from quad, we didn't use any of the information on the stack for quad. There's this whole region of information on the stack for quad. It has local variables. It has its argument. We didn't use any of that information. We just jumped immediately to its return address. We just returned right away from quad. That was not true for the green call to double. The green call to double definitely had to return, save something, save some local variable into the stack so that then we could use 20 and make another function call. And so that's the way in which these things are different. There was processing to do with the answer of the green call to double, and the orange call to double has this special property that we didn't need the information that was on the stack in quad after that call returned, and we just returned directly to quad's caller. We returned directly to quad's return address. So during the call to double, during the second call to double, I'm just going to underline it in orange. Once we start this call to double, we no longer need all of this local storage stack space for quad. It's just never going to be used again. We're done with it. We've done everything we're going to do with local variables for quad as soon as we start this nested call, as soon as we start this orange call to double, as soon as we start that call. So that idea that if we make a function call where there's no work to do after it except for returning the value, that's what I was summarizing at the end of class on Monday as a tail call. So the orange double call is a tail call. So it's in this special position where we don't have any more use for quad stack frame while we're doing it. Whereas this green call to double was not a tail call, because we were going to need to use the value that came back from it and still do more processing inside quad before we continue. So it's worth asking for a few more examples. This was a super simple example of the difference between a tail call and not a tail call, just this nested call to double. So it's worth asking in a few more examples, like which positions are tail calls and which aren't. So let's think about this for a minute, and we'll turn these into a few different questions. So let's say we have a function, and in order to determine the condition, it calls a function on that argument. So this call here, let me do another color. Is this a tail call or not? Five, four, three, two, one. Okay, talk about this for like 30 seconds. I'm going to draw another example while you talk about it. Okay, click in again, click in again. Five, four, three, two, one. Okay, So the question to ask about whenever we're trying to answer this question of can this position be a tail call is there any work we need to do with the results of the function call other than return that value from the current function? Is there any work we need to do between returning from the call to f and returning from the function g? Right? So it's a relationship between this function call expression and the function body it appears in. That's really what this is about. It's a relationship between particular expressions like f applied to x and the whole function body it appears in. In this case, we're going to call f on x. Then we're going to use the result of that as the value we check for the if condition. So the key thing there is we're going to use the result of that. That's going to be the thing we check. There's going to be like a compare instruction or some instruction that uses that value. Then we're going to go do more work to figure out the return value. Okay? So this is not a tail call. Not a tail call. I guess I'll keep using green for not tail calls and orange for tail calls. This is not a tail call because there's work to do with the result. So how about this one? How about this f of x in this example over here? Same question where A is tail call and B is not tail call. Five, four, three, two, one. Okay. Talk about this one for a minute. Also generate questions about the last example if you have any questions about the last example. Okay, click in again on this second one. Click in again on this second one. Okay. 5, 4, 3, 2, 1. And so this one, after the call to f, we'll take the answer to that, and that's going to we're going to need to store that in the local variable y, and then we'll use y in a later part of the computation. So this is also not a tail call because we need to do more work in the body of the h function with the result of the call to f. Right? After the call to f, there's more work to do before we can return. I'm going to actually, so I'm going to pause for questions for a minute, and I have one or two more examples I want to do. But any questions about these so far? Yeah. I mean in the context of hx, yeah. So f of x, we're calling fx, and then we're doing more work in the body of h before we return, right? Yep, exactly. Yeah. Yeah, this is the same syntax I've been using in lecture. Yep. So I'm just keeping the lecture syntax. No. This is the Cobra syntax would have the Cobra syntax is what I drew on the first slide with the fine and then the name and then the arguments in parentheses. Okay. So I'm going to tweak this first example. And I'm going to put another function here. Let's just call it sum. And let's ask, is this a tail call? So tweak that example. Is that a tail call? Is that call to sum in the else branch a tail call? 5, 4, 3, 2, 1. Cool. So most folks agree on this one, that this is definitely a tail call. Because in this if expression, once we check the condition in this if expression, we're going to evaluate the entire body of G to either the then branch or the else branch. One of those is going to provide the return value for G. So either one is either a call that appeared in either one of these would be a tail call. Okay. Actually, here's another question I want to ask. Did this change the answer? So if I erase this, did this change the answer to the f of x answer? Did this change the first answer we did? No, right, because we still have more work to do after this f of x. In fact, all we need to know is that this f of x is appearing in this conditional position that's in an if, and that's enough for us to know that it can't be a tail call, right? It's not like other things about the function. It's not like we needed to consider all those things about the function. This is not a tail call just by virtue of appearing there. If I changed this to f instead of sum, would the answer to if this is a tail call change or not? If this is a tail call change or not? Let's open that up. So erase this. I just change it from sum to f. Does that change if else is a tail call or not? Five, 4, 3, 2, 1. Okay. And I want to put this example up because it's an important point that it has nothing to do with f, right? I didn't even write the definition of f on the screen, and we were able to make these determinations about if these calls to f were tail calls or not. So it only has to do with where the application appears within the body of the function, not what function we're calling that affects if it's a tail call or not. So this is still a tail call to f, and we could have different calls to the same function, some of which are tail calls and some of which are not tail calls. It's just the application expression and where it appears that affects this. Doesn't matter what the definition of f is. So that's the definition of tail calls by example here. The handout from Friday has sort of traces this through as a Boolean parameter in the compiler that tells you at any given expression whether you're in tail position or not, whether the current expression has visited a path that would make it not be able to be in tail position, like being in the condition part of an if. And that's how we picked whether to pass true or false or pass on the tail call parameter in that implementation of the compiler. I'm not going to go through that on the screen. But the key idea for why this is useful, for why this matters, is that this comment here about this space being unneeded once we start the call to double, this means that there's another way to process this second call. Instead of trying to, instead of doing what we would typically do and make a new stack frame for this second call to double, we can avoid that entirely. We can avoid making this stack frame entirely for this other call to double and just reuse this space here. So just start, actually, it's probably, I'll just erase these to be clear about what happens. Just reuse this space here so that we get what looks like, these bottom three words here, look like the start of a call to a function. But instead of pushing an old EBP and a new return address, we just leave those in place and reuse the argument space. Then jump to the beginning of double. So instead of making a whole new stack frame, we reuse the current stack frame. Because quad doesn't need that space anymore. There's no way we're going to use that space anymore. That's the observation we made. Because all that's going to happen is we're going to call double, and then the return value from double is going to be the return value from quad. So we save the work of pushing a new return address and pushing an old EBP. We just overwrite the argument space and reuse the stack frame. And this is actually a pretty interesting, almost fundamental thing to implement for function calls. Can anyone think about why this would be really important? Why I'm emphasizing this, and I'm going to say this is not just an optimization. This is actually important fundamentally. Fundamental. Actually, think about this for like 30 seconds. Think about this for like 30 seconds. I don't just want to call on someone. Why is this fundamental and not something that's just some optimization? Why is this fundamental? It's not just making things faster. It's fundamental. Talk about it for a minute. Okay. So I'm starting to write out the sort of the examples we had, but does anyone have any reason? These are the examples we had on Friday. Any reason for why this is fundamental? Reason for why this is fundamental? You want to describe? You had a hand up earlier, but I want to know if there's any new hands. Go ahead. So it could allow, the comment is, I'm just going to sort of briefly summarize. You're saying it would allow us to do somewhat deeper, maybe even substantially deeper nested function calls or recursive function calls. Yeah. Any other comments? Yeah. Maybe this lets us implement something like loops because we're suggesting reusing space. Like loops, if you think about what a loop usually does, we declare some local variables, initialize them, and then we write this thing that never uses any more space, just rewrites those values over and over again. Yeah. Other reasons this might be fundamental? Yeah, so I think that the combination of these two answers gets at something that's pretty fundamental about having this in place for languages that use functions a lot. So if you write sum like this on the left-hand side, if you write the equivalent in C, and you try and call sum on some really large input, what'll happen? Like if you called like, and you can think about this in your current compiler too for homework. If you called sum on some big number, like 1 million, I think 1 million is where it starts to happen. What's going to happen? What do you get as a output? I mean, don't try and do the mental math. Yeah. Stack Overflow, which in our compilers, since we're in, the land of not actually checking this, right? This will segfault. You try and run this will segfault. You'll just go out of bounds of the stack space that the process has set up for you, and you'll get a segmentation fault. If you implement tail calls, right, you're not required to implement tail calls for your programming assignment, although we're happy if you do, but it's not required. If you do it in this style and have tail calls, this will actually use a constant amount of space. This will use a constant amount of space. It will use whatever space it needs for the local variables it figures out for sum. It'll use the space for n and so far. It'll simply use those 6 or 7 words of space and act like a while loop. It'll act like a while loop. And in fact, the generated code for it will even look like a while loop, right? It'll be a bunch of code with a condition at the top that jumps out of the loop and returns so far. And then the else branch will run the body of the loop, and then at the end of the loop, it'll jump back to the beginning of the loop, which is the beginning of the function. So a tail recursive function with sort of one tail call at the end that's a recursive call, with this proper tail call implementation turns into code that looks just like a while loop. I don't want to go through it right now. You can get GCC to do this. GCC will only do this for recursive functions. It won't do it for functions in general. So our calling convention makes it really easy to do this even for mutually recursive functions or just nested calls that happen to be in tail position. But GCC will do this for recursion. So you can get this optimization for recursive tail calls. So in GCC, this is called TRO for tail recursion optimization, or sometimes they call it sibling call optimization. And GCC will only do this if the function that's being called in tail position has exactly the same number and types of arguments. In languages like OCaml and JavaScript, this will work for any function call. The calling convention is set up in a way that you can reuse the stack much more easily. The problem in C's calling convention is that the arguments are at a fixed size below the place where we stored the return pointer. And so you can only fit a new function call that fits that size of arguments below that spot. So in GCC and C++, in C and C++, typically this only works for recursion or other calls that have the same number and type of arguments. Okay. Any questions about this idea? The thing we're doing, I would call, in the term of art for what we're doing, is called proper tail calls. It's not an optimization. It's actually sort of the right way to do this because it has the right space complexity, right? And there's no need to use a linear amount of space for a linear number of recursive tail calls, right? Or a linear number of tail calls, whether they're recursive or not. There's no need to use a linear amount of space for it. You just need the space for the biggest stack frame there. Cool. So I want to spend just a few minutes setting up the next topic that we're going to talk about. We're going to talk about implementing it next week before you have to implement it for the compiler. But I just want to introduce it so that we know what's coming next. And so far, the things we've talked about in this class are values like numbers and booleans with tags. We've talked about variables with let. And we've talked about calling functions. These are really the key compiler features we've talked about. And that's gotten us pretty far, actually. With if you add tail calls to the language, you have a general, like, totally Turing complete up to the fact that our integers are fixed size language, because we have recursive functions that have good space guarantees. So that got us pretty far. We're up to sort of a nice arithmetic-like language. But there's a key thing that we can't do yet. There's a really important thing that our languages can't do, which is we can't build any data structures in our languages, right? I mean, ints and bools, those are all 4 bytes long. You just can't build a data structure out of those things, right? They're primitive types that take up one word. And so the next thing that I want to talk about in the course, which is going to sort of round out our compilers so we have all the main interesting language features that we need to talk about optimization and memory management, things like that. So the next feature I want to talk about is heap allocated values. Really, what I want to talk about is structured data. Because the second half of the course is basically about the heap, memory management, and optimization. That's really what the second half of the course is about. And so to motivate this, I want to pick something, and the goal here is to pick something pretty simple. We could say, let's go all the way and implement classes, right? And that's like a really interesting thing to do, but we would spend all the remaining like 3 to 5 weeks implementing classes, right? It'd be cool to do, but we're not going to go all the way to implementing full-on classes. We could say, let's implement structs like in C. Let's just implement structs like in C. And we could do that. Part of the infrastructure that would require is a lot more stuff in like well-formedness, right? A lot more stuff in well-formedness and a lot more information in the environment. So you have to keep track of the struct and the types of its members and what the names of the structs are. These are also not bad things to do, but they also sort of add overhead that doesn't have to do with understanding heap allocated values. So what we're going to do is we're going to introduce sort of the simplest possible piece of structured data. Okay? the simplest piece of structured data. In lecture, we're going to talk about pairs. In the PA, so this is in lecture. In the PAs, that's going to be tuples. So tuples of arbitrary length. So one element tuples, two element tuples, three element tuples, and so on. Okay? In lecture, I'm going to talk about pairs, very similar to other constructs. In lecture, I'm going to do something that's simple enough that I can fit it on a page. And in PAs, it'll generalize to sort of the arbitrary length case. So we're going to talk about pairs. It's just worth reminding ourselves that pairs are actually a pretty powerful, expressive way to describe structured data. You can get really far with pairs. You can get really far with pairs. So just as a simple example of the kind of thing we're going to be talking about, we're going to introduce a new expression form called pair. And pair is going to take in two values, two expression values. And somehow it's going to package those together and save them somewhere. That's going to be the thing we're going to have to talk about implementing. And then we're going to be able to access those values by selecting them out by saying things like, I want the first element of the pair P, and I want the second element of the pair P. And you can think of these in, second of P, not second of 2, sorry. And you can think of these as almost being like square brackets 0 and square brackets 1 to get the thing at index 0 and index 1. There's actually functions called first and second defined in OCaml. This is how you can access these elements of pairs in OCaml. So those are going to be the 3 new constructs we add. And we're going to use pairs to explore how we set up a heap in a programming language's runtime. Like, whoa, we have to do that, right? We don't have a heap right now. We have a stack, but we haven't talked at all about that entire other region of space that we use that persists across function calls. That's the special thing about the heap. You allocate a value on the heap, it's around until you clean it up. Doesn't matter how many functions you call in between or how many loops you run in between, that thing persists, right? And so that's going to let us talk about that entire region of the runtime of a programming language, and we'll talk about managing that memory and some optimizations on it. So that's what's coming on Monday. The midterm that's on Friday covers up through sort of the simple one